Okay, so yesterday we were discussing how to design exchange correlation functionals. Okay, and there at some point we stopped that how these constants help to design those exchange correlation functionals. Okay, so today this I specifically designed today. So I want to talk about all those constants that should be exactly satisfied, or if they are violated, then what will happen. Okay. So instead of going to all these things, so let us do that thing, and in the hands-on, we'll see. We'll pick to one or two functionals. We'll see how these simple periodic table elements how they are behaving. Okay. If you want to calculate these atoms, or if you want to calculate these bands for some small systems like germanium, silicon, or whatever. So we'll be discussing this exchange constants. Okay. So Professor Chaturaj was asking how many constants are there. So I think I figured out 18, but I categorized them not in scan way, the way Purdue did. I did it my way. Okay. So the first one, so these are the list of constants according to John Purdue. So there are 17 constants. Okay, I'll give you all these slides. Okay. No, I'll go. There are the constants are there. So like it's a negative exchange energy, and its scaling will be there, and then bounds will be there, and then the other things are like high density limit, and those things are there. Okay, the first constant is uniform electron gas limit. Okay. So what is the uniform electron gas limit? So this is like you have this is kind of this spread out of this all this density, and then in the limit rho goes to rho 0, this constant, then what will happen? This exchange energy for the number of particles, that is the exchange correlation energy density. So this is, and what are the functionals? It's already there. So the LDA functional is built in, and then in the GGA functional here it's also there, and meta GGA there, and all these things are there. Okay, that is the uniform electron density. And then why it is important? So it is important because you have for a slowly varying density, it is important that you have to ensure this homogeneity. Okay, and then this is also affects the transferability. So if you want to calculate for molecules or solids, so that in that case also is useful. Okay, and any violation of this will have this, like in metallic system and other things, it is important. Okay, so this is the first constant, that you have to have this uniform electron density. So like this electron gas means whenever you have uniform electron, this homogeneous density, so this is useful. That is the first constant. If you are building any functional, okay, and in constant density, if it is uniform, the density is uniform, then this it should go to that domain. Okay, and what is the next one? So then the next one is the uniform density scaling. Okay, so what is this uniform density scaling? This is the density. Now you modulate the density by a factor of lambda. Okay, so this will look like this, say n lambda r. Then, but the number of electrons remains the same. Okay, so that is the constant it will satisfy. And if that is the case, then how this exchange correlation energy will scale? Okay, if you scale the density, how the exchange correlation energy will scale. Okay, if you are designing any functional, okay, so if you have this, so it should scale linearly. This one, this you can derive, and which component will scale, whether the exchange part will scale or the correlation part will scale. So that is the thing. It goes this correlation, you will be having rho 1 upon lambda kind of thing, and this one, this thing, this is the scaling of this thing. Okay, this is also, the scaling is built in LDA approximation, that is the ladder 1 of the Jacob's ladder. Okay, and this is also this also preserves the next run, the generalized gradient approximation, that also preserves the scaling, and then this meta GGA and all these things. If it is here, then it is also respect the correct scaling behavior. It goes like this. Okay, because see, while climbing the ladder, we claim that the functionals are better. If the functionals are better, they will satisfy more number of constraints. Okay, so that is the thing. Yes. Only exchange. This one. This is approximate way. I am right. Yes. Yes. Uh-huh.
Okay. Kinetic energy is a homogeneous function of degree 2.
Degree 2, yes.
And potential energy is a homogeneous function of degree 1.
1.
Okay. This you can say, the Euler's theorem you can show.
Yes, yes.
Now the question exchange, there is no trouble. Because it's a part of
in correlation,
Coulomb stuff, it would go as lambda to the power 1.
Yes.
Correlation has a problem because correlation contains one part which is kinetic energy, another part which is
yes, that is the TC. Yes.
So you cannot have proper homogeneous scaling for the correlation. That you must know. If you can separate out two components separately out of correlation, one is kinetic energy part, another is potential energy part, then separately they will scale as kinetic energy go lambda square and this will go as lambda.
That is exactly what is happening in meta GGA onwards.
Yes. So this is something
what that is why you are
going. But when you write EXC n lambda as lambda EXC n, I think it is not right.
Here I have written something. Here in correlation, there. So that is it's approximately, I said. Okay. So sometimes these are required to the audience will get involved. No, that is true. That is true. So I want to give a not very rigorous thing of these constants. Okay. Now, so this is the second constant, that is how if your density scales, okay, so then you have to have functionals which will appropriately take care of this density scaling and so that it will get better. If the functional, keep in mind, if the functional satisfies more number of constraints, okay, the functional construction is so that it will satisfy more number of constraints. That means the functional is better. See, the functional, this one was given long back, this is LDA, when Hohenberg cone paper or Dirac thing. Now this scan came in 2015. Okay. So that is the thing. Scan satisfies almost all the 17 constraints. Okay. That is the thing. What is next? Then the spin scaling relation. Here you take, while you do the spin, then local spin density approximation or spin polarized calculation, whether a system is polarized or unpolarized and all these things, then how will do. Okay. Now what is happening, if you write down this exchange energy, this is the spin polarization you can see. So these are the upspin and downspin. Then you write down the spin polarization. So what is the constant is exact. So for exchange, this is the spin polarization. Okay, and these are these conditions. Okay, now why it is important? Because it ensures correct behavior. As I said, the spin polarization. Okay, from unpolarized to fully polarized. So when you have that kind of thing, all the systems are not closed structures like carbon. Okay, but say lithium. Yes, so that is where it matters, the spin scale. Okay, upspin, downspin, and then upcharge density, downcharge density, and all these cases. Okay, so now, so what is happening? This one also having this thing, and then this GGA, meta GGA, they also have the spin scaling relation remains intact. What these are the satisfied by all runs of the Jacob's ladder. You satisfy round 1, round 2, round 3, like this. All these things are satisfied. Okay. So the spin spelling relation is fundamental in nature. Okay, that is what I said. So what is happen if you have a good exchange correlation functional, okay, then it must respect the it at every point in space. Okay, the spin scaling should be satisfied. Okay, so in a way it helps us if you have these magnetic systems and other systems. If the functional is not behaving properly with respect to spin thing, then you cannot speak of all these things, spin chirality and all these things. Now they are talking spin turn is altermagnetism, all this, then that will be in soup. Okay, that is the thing. So far clear, 3 constants. Now we'll go for another 15 constants. Okay. So this one is a second order gradient expansion. Yesterday I show you that you develop this exchange correlation functional with an enhancement factor, okay, F, and that enhancement factor you have seen yesterday, that kind of form, okay, this one, okay, and there are some factors which were there. Now when you have this thing, okay, see this density is rapidly oscillating, and this is like there is not much oscillation here. Okay, if that is the case, then this inhomogeneity should some way be incorporated or embedded in the functional construction. So how that will do? How will do that one? Yesterday we were saying that everything is taken care through this enhancement factor, or how you are designing your exchange correlation hole. Okay, when she was talking something in this density matrices, I heard something. So you'll be having this density matrix expansion and other things. When you have these expansions, there are the single pole, multipole, all these things will come, this response function. This also similar kind of thing, this gradient expansion, whether you can have an exchange correlation hole, then you expand that thing, or you can have the plane wave expansion. Okay, so that is the thing. You have a Fourier space kind of thing. So that is called GE2, gradient expansion of second order, GE4. So here I have taken into account the second order gradient expansion. There are in the scan paper, it is also written, or in some modeling, material modeling or somewhere he has mentioned that this G4 also is required for scan thing. But I don't want to go there. Let us think, because the Purdue, this Becky thing was at G2, so that's why I have taken into account. What I like to say, you have it at the level of G2, then you do something else. Okay, it will not make your life complicated, but at the same time the functional will be simple, and the enhancement factor, the functional form will be simple. Then it will be better, it will be easier to do the numerical differentiation, functional derivative, while you have to have the exchange correlation potential or this del E x by del rho in some way. So in that sense it will be useful. The more simple will be the functional form, it will be better. Yes. Yes. Because the spin scaling, this exchange is due to the spin, so that is the thing. Yes.
Usually, if I make the exchange functional for gas which has zero polarization spin, then I can always do this.
Yes.
So how this becomes a requirement? I mean, this will always follow, right?
No.
Because you don't make the left one separately and the right one separately.
No, we don't do. But what I said, that these are the things he listed it out.
Okay.
Okay.
Thanks.
That is the thing.
Thank you.
Yes.
But it should be required to do polarized DFT calculation.
Uh-huh.
Polarized DFT you are separately you are solving quantum equation for upspin and downspin.
Yes. Yes.
Spin polarized.
Yes.
Separately solved.
No, so, in some cases, if you have spin resolved density of states and other things, there you have to do. When you have this isoorbital indicator, electron localization function, there, that's why I said, na, if you don't have this inbuilt kind of intrinsic way of taking into account spin, which is not there. If you have to take into account, you have to take several things. You have to take SU2 symmetry and this gauge invariance, all these. There is some functional. Yesterday we were talking with Ranjit. Yes.
Variable x
Uh,
r comma sigma, but for all practical purposes they are different.
there,
Nowhere you are getting a common like under the same bracket r and sigma.
R and
Sigma we
sigma,
are putting always by hand.
you are talking about.
Wherever you are doing calculation in non-relativistic
Uh-huh.
sigma spin variables never come explicitly into a Hamiltonian or Thomson operator, Hatipov operator. No.
No.
We are putting it by hand.
Yes, yes.
So that's why.
That is the Jai you are talking.
Yeah. So
That will also come.
So what we are doing in this case, as you are like to n alpha and to n beta, you can separately do the calculation. That's what people do is spin polarized DFT.
Yes.
You solve for some for upspin, for some for downspin, and then do whatever you like. You can spin potential, spin density, particularly spin density used by all inorganic chemists today. For explaining many of
If you are doing this pure thing, what Bhamsi said, it is also you are using hybrid functionals. So in that case, there is some mixing is there. In a hybrid functionals thing, when you do double hybrid with this MP2 and other things, so suppose you take this CISD or Slater determinants or something, then you go from say atomic, say all electron calculation to PAW, projector augmented wave or something. There they do something in vast.
whatever you do, even if you got the Slater determinant, your elements of the Slater determinant are spin orbitals, but the spin function is put by hand. It is not coming with the orbitals are coming through some self-consistent.
Yes, yes, yes.
Spin is not coming. Spin is
No, there the spin is not coming. That is true. What I am saying,
and unless you
He's talking about the constraints. So that's about it.
I know separation of upspin and downspin. That's what it is. So where are you getting the concept of upspin and downspin?
It is artificially built by us. Yes.
So that's okay. That's besides the point. Even if it is
sir. Hmm. No, we are taking this SVN, na, Vorsco will psi Vorsco formula with this quantum dynamical Monte Carlo thing. We are fitting and having that form. So that is also for HEG, that also the same thing. Yes. Yes, yes, yes. Any question?
When we have the Kohn-Sham equations,
Hmm.
the Fock operator depends on both up and down spin.
Downswing.
So the density is a sum of both of those terms.
Yes.
So it's not really decoupled, upspin and downspin equations.
That's what I said. When you have this hybrid functionals, there is something it is having because you have this exchange operator, this. That's what I said. Are you using this hybrid in that sense you are talking? Xi is spin polarization. So it's a rho up minus rho down by total rho. So if you have this spin polarization there in the enhancement factor, if you have to have some functional say magnetic or that thing, then you have to include current there, current density. Okay, so that is the thing. And this current density they stopped probably this Vignale, all this and this all go this cone all this and this. CTDF. So where we stopped? So this one we already have this. Now how? So this is exchange energy and correlation energy. Are they positive or negative? Hmm? Exchange correlation energy positive or negative? Any question? Any response? Or it is zero? Huh? Who said? No, you said you are working with. Yeah, I'll ask someone, a student of Samal, Chaitanya. So I am asking that we are gathered here, so many things, so like lectures gone. Now I am asking, I am saying exchange is zero, a correlation is zero, exchange is negative. Am I right or wrong?
We have to the mobile take a picture and show it to them. This is how they respond.
Huh? Today in this practical session, you will be allowed to use your mobile phone, everything, chat GPT, everything. Will derive a functional and will take this thing we have to answer today. Whether it will be a negative or it will be positive or what, which is zero. See, none of you are opening your mouth. Positive or negative? Zero. Negative. Why? Suppose I am in the Rydberg state. What will happen? Or auto-ionized state. Let's not talk about this ground state. Then you are
Let's consider your exchange energy.
positive. Then what will happen?
Then you reduce back and show that whether it is right or wrong.
So this constant tells. So Elliot Lear, and then he's a famous mathematician. Okay. So it says that it will be negative. Okay. It cannot be negative like anything, infinitely negative. Okay. There should be some bound on this one. It cannot go beyond that thing. Okay. So that is called, it's giving a bound on exchange correlation energy. So that is called Liev-Oxford bound. You look at here. Okay. So here it's zero. It is going, then it's minus infinity. What it says, after there is a boundary beyond which that value cannot cross. Okay. It cannot go down, that is not possible. And this is giving this thing. Okay. So there is, like if you put it like this, then there should be a balance. This is the exchange correlation energy, and there is a bound here. 1 kg, 2 kg, 3 kg, it cannot go beyond. It is balanced, perfectly balanced. It cannot go beyond that. Okay. So that is the thing. Okay. So and it is also satisfied by all these functionals, LDA, GGA, meta GGA, hybrid, and all these things. All these obey this thing. Okay. And if it will not, then the system will become unstable. Okay. And it will have unphysical collapse of the system if it will go forever negative. Okay. So that is the thing. Okay. This is a must condition for all the functionals to satisfy. Okay. That is the thing. I'll give you all these slides. No need to write. Okay. That is the thing. That it can be derived. That physically means you. I think I forgot the real way. Recently there is a paper. Not recently. I think 7-8 years back. No, there is this, this Burke and Co, they did something recently. They again make it more tight. This Klaus Capel, he did something. Then after that, I forgot the exact thing. So that is the thing, that it should be, there should be some bound. Otherwise, it will have this behavior, unphysical behavior, and that is called the tight bound on the exchange correlation energy. Yes. Now comes the positivity of the enhancement factor. Okay. Now what you look at here, yesterday I was telling, this should be positive and these are the functionals. Okay. Now this is from 1, it is decaying, and but this is physically, okay. This should be positive, and if it will be negative, then this is the case. And if it will be negative, then you look at here, your exchange is already negative, this uniform density exchange energy, and if it will also negative, then that will become positive, and it will contradict to what? Lie-Oxford bound. Simple thing. There are other strict conditions are there. Okay. Now this is the simplistic way of looking at this thing. Okay. And here this satisfied. Okay. And here this, all these enhancement factors, they also satisfied. The positivity of the enhancement factor. Okay. That is the logic. Okay. The simple logic. Previous one was this Lie-Oxford bound. And now this one, if you have this thing, then that is the thing. So this is the, so how many constant do we finish? The 6. Any question? Universal. That's why I say, no, I don't want to make statement when he asked, because I have never derived that paper. But that paper is rigorously mathematical. Also, the constant search paper of Elliott, I think he's very sharp in mathematics. Or okay. Now the constant 6. See, if you look at our any wave function, the hydrogen wave function and other thing, if you do the density, how are the wave function look? Exponential minus r upon a naught, the Bohr radius kind of thing. Now, if that is the case, the density also goes exponentially. If you put it in the exchange correlation functional, so it will be exponential. Okay, that potential or whatever. But the actual scenario is that it should go like this 1 minus 1 upon r. Why it is required? If you look at here, this is the exact behavior. This is the GGA, LDA kind of thing, and this is the Hartree-Fock. Why Hartree-Fock is useful? Why it is called exact exchange? Because it has this minus 1 upon r, the correct asymptotic behavior. And what is the difference in Hartree-Fock orbital and quantum thing? Your quantum chemistry and this thing, that it satisfies something called Koopman's theorem. Every orbital has physical meaning, okay, when you do this Hartree-Fock and other things. But the quantum case, only the outermost orbital has the physical meaning. Okay, you can talk of this ionization potential, electron affinity, and all these things. So electron removal energy or addition energy, you can talk like which orbital the electron you are adding or removing, that will be like the Hartree-Fock eigenvalue, negative of that thing or positive, those things. But in quantum it is not working. So why it is required? If you have a correct asymptotic behavior, okay, then most of the properties can be well described. Okay, otherwise it will become nonsense. Okay, so that is the thing. You have this is not asymptotically, this is not correct, and this decays very fast, and then there is no, sometimes it will satisfy, some functionals it is not satisfying for meta GG, but in hybrid it is there, at least for exchange, because you are having 1/3 of the Hartree Fock exchange. Okay. Yes. Yes. Yes.
So when you say physical significance, that -1/R tail arises from exchange or integrating to -1 electron, that's perfectly fine.
Yes.
It must. But in LDA also, the whole integrates to -1. So
Yes.
an additional condition is it should be left behind in the system. The
Yes.
whole should not move out with the
Out of the
with
this-
the electron.
with
If
the
it
electron.
centers around the electron, then there is a problem.
problem. Yes.
Just wanted to make that.
Yes. Yes.
I had a question about this first one. Essential for accurate ionization potential. This ionization energy supposed to be the energy orbital energy. So this is the ionization energy that you are getting with the orbital relaxation of the system, the true ionization energy, or like Koopman, just the taking out the electron without relaxing the.
I think it's like the Koopman.
No, that's DFT is exact.
Okay.
DFT, the highest occupied eigenvalue
Is the outermost thing.
always -1.
But in additionally in a Hartree Fock is having, you can go inside also that removal or addition.
That is Koopman's is approximate.
Yes,
without
yes.
relaxation.
Mhm.
Here, no matter
Here,
what.
yes.
It's the exact.
Here is the SCF calculation by default. This it's already relaxed thing.
Yeah. Ionization, yes. Only the home.
Janak's theorem.
Which tells you that Janak's theorem, you can talk about del E del NJ. You can calculate that one, where E is the total energy and NJ is the occupation of
The
the jth
yes.
Consum orbital, and that is same as the molecular orbital energy of the jth Consum orbital. That is Janak's theorem, and that is exact in DFT. So in principle, you can calculate, apply Janak's theorem to do this job, but Koopman's is not applicable in DFT, except home.
This also there is interesting thing when you do OEP OPM. Okay, in that thing also you can think it's standing somewhere in between this DFT and Hartree Fock. Optimize effective potential and optimize OEP OPM. Tolman schedule. Also this Purdue also worked to find out the potential in an iterative way. Then with Stefan Kummel, what he stopped. Yes. KLI OPM you are talking? Yes. NOS did a lot of work. You ask.
What does it mean that DFT, the electron removal energy is exact? For example, if you
No. Who said it? No.
The only uppermost orbital is calculated exactly is to the exact ionization. That's all.
No. You whatever functional you take, that is the outermost thing. You are saying you are
Exact. In exact, it will be exact ionization, but others you don't know.
yes.
That's true. Koopman's is applicable only for the exact.
Yes.
So if you have anything approximate, everything will come.
Non-local and all these things restricted and
That it should be exact.
yes.
So exact.
Is there a constraint on the correlation potential?
No. There is
Correlation, yeah, I can count. Correlation potential goes as the polarizability of the ion divided by R raised to 4. That also can be proven exactly. But correlation potential dries down much faster than 1/R because correlation pole is zero charge.
zero. Yes. So you integrate that is zero. So most of the things are lies with this normalization and other. That will come the next thing. So I have Anand. Okay. So now one electron self interaction error. Okay. So if you have solved this, I don't know whether you solve this hydrogen atom, there is only one electron. Okay. But still you can use the LDA, GGA, all these functionals to calculate the hydrogen energy. How that is happening? Because that is one electron. Okay. So you think in that way. Okay. So what is happening if you have one electron? Means there is no exchange correlation. So it should be somewhere it should be vanish. So this E hat-tree for the single electron, and if you have this E this exchange, this should be 0, and then you accordingly you will have this for one electron. This is the picture. So it's LDA fails. This also fails. This also fails. Okay. The one electron approximation, it is not 0. Okay. So you have to make the self interaction correction. That is something which was given by Junger. Okay. Before that also there was some other thing for self interaction, that is called Fermi-Amaldi correction. Okay. Recently they are also they are now recently using the Fermi-Amaldi to do the self interaction, one electron self interaction error correction in advanced density functional, because it is easy. Yes. That meaning it's like the self energy kind of thing which should. Blind to is number of electrons, density. Okay. No, this fails for LDA. If you say hydrogen atom, it is not 0. But we are using LDA, and if you in any code you do, if you are using Gaussian or other thing, you take LDA functional, you are calculating minus 13.6 electron volt. How it is coming? This, but that is fine. But I am using the functional. It should not be there. There is no exchange correlation. Nothing. How that is happening? That is the thing. Because we are while doing all this, we are not at all thinking of the how many electrons are there. Okay. Then there is something, I don't know if you look at this course, this virial theorem. Okay, 2T plus V, that thing, that is also used. Because if you are using this application, means using the code as such, if you are not developing this thing, inside this SCF atom, all these things are there. Here is, what is that? The Hermann-Skillman code and other thing. If you look at there, if you are using, there are today you can go and check with this Hermann-Skillman code that is available.
So suppose you take hydrogen atom, right? And in hydrogen atom, take the density, which is exponentially minus R, right? You calculate the electrostatic energy of it. You calculate the exchange energy. But there should be none. They should add up to 0. If they don't, then you're making an error in the function.
Functional, yes.
That is what.
That's what I was telling earlier, that this exponential decaying, you have exponential minus R upon A naught. Then you you calculate the Coulomb integral. You calculate the exchange, LDA exchange, then you add. See what is happening. Or you take like Li2 plus, okay, helium plus, all these things you can do. Okay. So that is also important. So this is up to here, there is this problem. Then you have to do this self interaction correction thing, but all these things they satisfy. Okay. So this is also a major issue. If you have to look at all these things, this self interaction thing. because most of the time you are using like this comparing with MP2, like this CCSD, CISD, and all these things, GWBSC. But you have to look at how whether your functional is behaving properly with respect to all these constants. You can't simply say that LDA PB underestimates band gap, it does overbinding and other things. That is the problem. That's why this scan functional came, R2 scan, all these functions. Yes.
So one of the main problem in tackling self-interaction is the main reason for self-interaction error is that the artery potential goes as a rho square. If you say decrease the charge uniformly by half, then the artery energy would go down as 1/4.
Hmm.
So to correct it, you must design a functional say that goes as rho square.
Hmm.
But in the UEG limit, it must only go as rho 4/3.
Yes.
So I'm just thinking, is it even a possible construction that everything goes as rho square, but then goes as rho 4/3 UEG limit?
So you want to interpolate something like that?
I'm asking how, if there is a solution to this problem, if there is a
So,
algorithm to solve this.
so far not. You start one problem. Now this is the one. So, what is this correlation whole normalization? Okay. So what is happening? So if you look at here, so you look at this phenomenon, this exchange phenomena and correlation phenomena. This exchange tells that is this electron, same spin electron cannot be around. So it will be like there is nothing. You will not find out anything here. It's a shallow, deep thing. And what is happening in correlation? If it is not here, it has to appear somewhere. It should be compensated somewhere. That is the thing. It's not here, but it is compensated somewhere at some other place. Now this is the mixing thing, and this is the this sum rule, this normalization thing you will be having. Now, if you look at this one, okay, there is this thing, this uniform electron gas limit. If you look at things, so how it manifests across this Jacob's ladder, this exchange correlation whole physics, okay. So if you look at this is the density profile kind of, this is the exchange correlation whole, it will be like this, something like this, you'll be having. And why it is this important? Because you'll be having this, what is that, in, see, you can, if you can come up with a good exchange correlation whole, like your Coulomb interaction or Hartree thing, you can write down this rho xc kind of thing. And if you take properly into account all these things, most of the problem will be solved. Okay, that is the thing. So if there is an inhomogeneous system, most of the systems are inhomogeneous. If you properly construct this exchange correlation whole and it will satisfy all these things, okay, then it will be several things. It will be whether you having dissociation or this what is that band gaps, okay, and this Stokes shifts, photoluminescence, all these things, charge transfer. So it will be helpful in that way.
What is the physical feature of this one?
Which
Is it
one?
something similar to RTF, like IWTC?
This is like, this is the behavior. If you look at this exchange correlation whole, this would behave like this. This will look like this. If this is not schematics. For this one, if you have this exchange correlation whole, say for Becky, you'll be having something, some structure like this. If you do this plotting. Hybrid, it's like you are having this independent kind of thing. You have this Hartree-Fock and other thing. So it's mostly this Hartree-Fock Hartree exchange, this exchange hole, the exchange integral, you are having Hartree fog, and there is this exchange hole of the, what is that? The exchange part of the density functional approximation. So there it's not something you are going to, it's by default you will be having all these pictures in the, if it is Hartree fog is there, it's mixed, it's somewhere it's taking into account in the SCF calculation, this part. So that's why this is not something, this is like, it's perfect for hybrids. You do local hybrid or global hybrid, as long as your Hartree fog is there, then no problem. And if you have this thing, when you are talking of this exchange correlation hole, you have used this say highly accurate quantum chemical methods.
It's like say buy one get one free subscribe.
Buy one get one.
Like you are getting good exchange, so automatically correlation. What is the connection? You know that there are two different.
Hmm.
But you are telling that if you improve the exchange, automatically correlation will be.
No, it's not.
No, that's what I mean. If you have proper exchange, you get better.
Proper exchange, I'm telling that this exchange correlation hole
Here also the exact exchange improves.
is that is the thing. Correlation, no, correlation is this, the way it's the normal, this is the integrates to 0. There is nothing lying there. Probably if you use something like dynamical thing, like a time dependent or something, maybe non-adiabatic, I don't know how. Huh? Is hybrids is it's like because of this Hartree fog thing. Then if you do the self interaction corrected this exchange part, is no, it is not doing, but why doing that is a
That's what he means, I think.
Hmm.
That's what he means, the overall improves, that's what he means.
See, this hybrid also, unless you do GKs, generalized cone something, things will not come clear. GKs is, that's what I'm saying. So GKs thing, you will always, you have to look at for that thing. Okay. So that is the thing, and this is another picture of the same. You are asking now this. Now you look at this exchange correlation hole, how it will look for this GGA, meta GGA, and all these things. Okay. Now, so if you look at this electron is here, and this red thing is like your exchange hole, and the other thing that if here some density, there is some depletion, and there is somewhere there will be accumulation kind of thing. This is another picture for that thing. Okay. So that is the thing. I have one more slide on this. That is the thing. Here, only thing is that here I want to say that for this solids also, why this one is working so well? If you have proper exchange correlation hole, that's why this Becky Johnson, modified Becky Johnson, why they work so well. Okay, because they use this Becky Russell thing, the potential this exchange correlation thing. So that is one thing. So here, because of this thing, I mentioned this slide. So now this one we already discussed. So this is the local spin density scaling. Okay. What you see here? Can you make some analysis? What is happening here? And I was telling now this Xi thing, we are talking initially the spin polarization, that is the Xi here, and so on. Okay, perfectly polarized and unpolarized. Okay. Now what is happening? Local spin scaling means you have to have this thing, this polarization that should appear in this enhancement factor here. Okay. So that is, if that is the case, then the spin spelling what or scaling what we are doing before, then that will have better that will have give a upper hand if you use this spin scaling, okay, in the functional construction. Okay, so that is the thing. Okay, so it will your enhancement factor or the way you design the functional, it should have this thing. Okay, so that is like you have this polarization, this thing, the Xi, how it will be for this schematics. What should be the Xi? Okay, these are the upspin, downspin. Okay, like here it will Xi 0, is polarized Xi 1. Okay, and all these things. And if it will be violated, then this is the problem it will have. It will give you everything wrongly. Okay, so magnetic moment, band gap, okay, and this bond dissociation, all these things will go wrong. Yes.
Since you write an enhancement factor for every exchange or exchange correlation, and so you necessarily improve the local energy density, right?
Yes.
Or do you look at it globally?
Why locally?
No, because this appears to be a constraint on improving it locally.
This Xi.
This Xi or local spin. See, earlier you had a constraint that E row up, row down should be equal to half E2 row up.
Yes, yes,
So that is a global condition.
yes.
Is this a local condition counterpart of that?
There are several cases where they are not taking into account the Xi at all.
No, so I understand that.
Yes.
So in writing that way, one has taken Xi overall into
Overall,
account.
yes.
So this is an additional local condition. So does that put a constraint on FX? That's what I'm. No, it's
No,
overall.
no. This is overall.
Overall.
This is overall.
So you understand my
Yes, yes, yes.
problem. Is it a constraint on FXC itself? Because that may be globally you may be improving, but you want locally correct. Is that a correct way of looking at it?
So that one, if you are doing this spin polarized thing in that way, half this,
Yes.
that thing, but this some way helping. What is that? Your kinetic energy density is also local.
Yes. So what I'm saying is, how does this become an additional constraint? So in addition to that global, you want a local correct also. Is that?
Yes, yes.
That is all my
Yes,
question.
yes.
Okay. So that there are two different constraints.
Yes,
one is local,
but
one
you
is
have to have the two things. Somewhere it should be somehow it should be taken into account. But in major cases it fails.
What fails? This one or that one?
No, which one is failing? That is not perfectly known.
So this is your experience in developing your functions.
Our functional, I don't know. So we have taken into account this costless hydrogen density, and somehow it is working. We don't exact
This is an additional constraint on the
local, yes. And this is also useful, the designing of the hybrid functionals, where you have local hybrid and global hybrid and double hybrid, screens and separated hybrid. So many hybrids are there.
By the way, I'm asking questions on your behalf. You may comment further if you don't understand. Because it's for you, it's not for me. Asking so that you provoke you. Can you
Tell. Which two?
Like satisfaction of the local constraint automatically will satisfy the global constraint.
No. Local will satisfy global, but come to, yes, the reverse we cannot. Global. So that is how it is. So you are having a locally homogeneous thing. Yes, So this, if you are using this jar, it's perfectly taken, then that is also fine.
That's why I was thinking, why 18 and 17?
Why 18, 17 inch?
No, but you told 18 constants.
Ha ha ha.
And if you scan, you have
17.
that one extra.
No, I thought the extra in some other way.
So, so I was thinking this is spin polarization can be a very, it can be, what should I say? It's not always a good quantity in DFT. For example, if you have something like open cell singlet, where this should not exist, but in DFT it exists.
Yes.
So having a constraint based on that by itself can be a problem. Isn't it?
There is this, if you are gaining somewhere, so that is the problem. See, that is the problem with the Becky category functionals and Purdue category. Purdue looked at it thinking of the surfaces and solids and all these bulk materials. But in your case, you are looking at molecules, clusters, and that thing.
Mhm.
So the paradigms are bit different there and here. That is the thing. And if you properly do all these things, see, inhomogeneity means if the density becomes inhomogeneous, why it will be in the ground state? Not, it won't always be in the ground state.
Which one become on?
Any case, excited states. Have you ever come across the excited states which is homogeneous?
No, it will never.
It will not.
No.
But you are doing this inhomogeneity is driving from this thing, but still you are remaining in the realm of this ground state thing, everything.
You see the papers by inorganic chemists, particularly who are using heavy elements, magnetochemistry, etc. So in that, you are with Rajaraman anyway. So dysprosium or something. Now, but there you can see their use of spin density in explaining. And I explained what is spin density, as not many people know what is spin density. So spin density plot, how you do, that takes care of the difference between your upspin and downspin. So in this situation, polarization or whatever you say, spin density, how it is derived, how it is calculated, and how it is used to explain certain magnetic properties or other properties of spin-dependent properties of the systems. So there are many, many papers now you can get. Even from Frank Nisse's group also there are many good papers.
I specifically say about open cell singlet because there in that system. Open cell singlet you do, but see, in open cell singlet, the spin density should not exist. In DFT, because alpha and beta, there is exactly same. It's a rho. If you go to like exact density, then it is rho alpha and rho beta both are rho divided by 2. So it actually spin. Yes. Yes. But,
You have some accumulation of plus density. Here you have accumulation of minus density. But you are doing it point to point. So in these points, when you are subtracting beta density from alpha density, you are getting somehow.
no.
Here also you are getting somehow.
So that
That difference
no,
makes you zero because it's a singlet.
no, even also in like instantaneously in every point it is 0 because we don't get an EPR signal from like in experimentally we don't get an EPR signal. Okay, sorry.
No. That is one more thing. Na? This low-lying states of given symmetry, that we are also forgetting. That is the paper of this guy. That if you, what you are talking, this excited state thing, you have to make sure whether you are, that is a low-lying symmetry of excited state or not. How far off from the ground state, or it is just slightly off from the ground state, the singlet you are talking. That also matters. Yes. So, Cassidawar, I forgot that name. Low-lying state of given von Barth. Hmm.
not amenable through the excited state DFT.
Yes.
It gives only for the ground state of or low lying
States of given symmetry.
energy state of
Given symmetry.
Or in an ensemble, at most 50% would be from the excited state.
Yes.
In no other cases, you can extend the Van-Wert theorem to the excited state till today. I'm telling you. But when you talk about the spectroscopy with 3DFT, they are doing it for all possible excited states.
That's how this ensemble DFT came. No?
Yeah, ensemble also. That's what I'm telling you. Ensemble DFT like crossover cone.
Go come.
They have shown that at most 50% from the excited state. The ground states must be minimum 50%.
And also that excited state may not be arbitrarily any kind of excited state.
No, there is no.
Yes.
In ensemble,
There is no restriction. Why?
only you go to pure excited state, they notice the lowest state of the given system.
What on?
Exchange, it is known that the spin scaling should be that as we discussed before. For correlation, perhaps it is different. For example, in NPTEL it is very different. So, if we write the exact functional like this way, we must have a way to separate the EXC part into exchange and correlation part, so that we can treat their spin scaling differently.
In correlation, why you bother about spin scaling?
But that will be affected if the, for example, if there are 5 electrons up and 5 electrons down, the correlation energy will be different from say 7 up and 3 down. So that is
From this exchange correlation perspective, how you are developing these functionals. So it's like this polarization of the spin, it will affect the correlation because of the distribution, correlation energy. But if it's not like that spin, like it has this thing, how the spin orientations and other thing, that is different correlation. So what you are saying there is a different scaling for correlation in terms of spin. What is that scaling?
that is not known. But
That's what I'm saying. So that is not known means that is not there.
for example, ATA correlation, say for example, Purdue and Purdue London correlations. So they have a different recipe to incorporate design.
Okay.
And that is different from how PV is doing
Yes.
for correlation. This is not followed in exchange.
No.
For exchange, it is known that you treat the up and down spin separately and then you scale them
Yes.
the known way. That is done exactly. For correlation, it is done differently. So
Yes.
that is what I'm saying, that if for example, if say correlation, if assume that they are nearby the exact spin scaling, then the exact functional should have a way to separate out the exchange and correlation part so that it can scale them differently.
But they are scaling different, you are saying, no? For this thing, PW91, PB, they are different.
So I was saying, like I was saying earlier, that this constraint, perhaps I think that EXC, there should be a way to, I'm saying two things now. That EXC functional exact, perhaps it should be separable into exchange and correlation.
Yes.
And this constraint perhaps applies only to the correlation part, this local spin scaling. Because for exchange it is exactly.
Why you want to separate the enhancement factor for exchange and correlation?
Overall functional, not just the enhancement factor.
No, overall, how will do that thing? This is having this EXE of this uniform thing. Then you are having a single enhancement factor.
That is what I think. But for example, in practice, you write NDA. For example. So you write exchange separately, EX, then and plus EC. For example, you do PB. So you write EX times its enhancement factors plus correlation minus some correction. So you never write EXC times some enhancement.
Enhancement.
So you never write epsilon and exceed the combined density times.
These enhancement factors are different.
So
Yes.
that is what I am saying, that perhaps the exact function should be separable in exchange and
That is already separated. PW921, you have correlation. Similarly, you are having PB correlation. You are having LYP, Li-Yang-Par correlation. They are separated already. That enhancement factor. And the what
General form.
is that is no, that is like the generic form.
Generic, that's what it is.
actually most of the non-functional it's not that
Exchange correlation together.
You tell any, you tell decade, you tell Kapati one, you tell PP, you tell B, all are either exchange or correlation, not that they are some.
Recent ones are like that.
They are specially designed.
What?
Recent ones like Minnesota one, MO6, they have
Yes.
this combined.
Yes.
Strange, it is because you don't want any physics. You have so many parameters. Whatever you call it,
Yeah.
you can call it character.
Yes.
No, he's from you're from Minnesota.
Functional myself.
Minnesota functional.
He was talking about that thing M06.
Based from that group. You are the 52 parameters. So 52 parameters will fit everything.
Okay. Now the exchange whole sum rule. Here what is happening? So we have already seen this, how this exchange whole will behave. Okay. So here it's a picture that these are the spin up. Then you are having a off spin. Then there will be some down, spin is there. And this is how you write down in terms of the exchange correlation whole. Okay. And what is happening? This thing. So this is very important for this this exchange whole sum rule. Okay. And this is also this exchange whole sum rule also helps you to, it's also somehow connected to the self interaction error, quasi particle, and exciton binding energy, and all these things are there. Okay. Like you do this exchange whole physics, you can do dielectric skinning, Linhart skinning, all these skinning things also comes into picture. Okay. Our recent work where we use this one, okay, to do this intrinsic skinning of this dielectric dependent hybrid or something. So that there it was. So that's why I categorically had this exchange whole sum rule. No. So it's like a mix of these things. So he has the something. Okay. Now comes the coordinate scaling. Okay. If you scale the coordinates, okay, say by a factor, say gamma, then what will happen? Okay. So it's like if you scale the coordinate, initially it was not scaled, then you scaled it, so it's like fragmented out. Okay. It's going, so you are multiplying some scalar to the coordinate. Okay, if I am here, you multiply me, then I'll go something else. So it is like spreading out these things. Okay, and this coordinate scaling, if you look at this one, so how this behaves, this coordinate scaling, how it affects this LDA, GGA, and how it behaves across the Jacob's ladder if you use the coordinate scaling. Okay. And then because of the scaling, how this exchange energy, exchange correlation energy behaves. Okay. So that is the thing. This is also important for where it will be important. So if you say there is a charge transport, okay, there in those things.
These are all exact scaling.
Yes.
Like density is 3, degree 3,
Yes.
kinetic energy degree 2, potential energy degree 1, and accordingly exchange is degree 1.
Degree 1.
Yes, so but correlation, as I told you, we have two components, kinetic energy and potential energy. So one goes as 1, another goes as 2. Together they would be somewhere in between 1 and 2.
Now you are focusing on orbital free DFT. because there we also do this scaling, this orbital free DFT,
Correlation should be somewhere in between 1 and 2.
one
It's a mixture of
kinetic and this.
greater than 1, less than 1.
le-
That can be shown very easily. Kinetic correlation. Kinetic energy, you see, there is a T minus Ts.
There is this exact kinetic energy
T
and then
minus-
some kinetic energy, T minus
Yes,
T.
this is T. It's a part of kinetic energy, and as kinetic energy goes as T is
Say
degree
the-
2.
what
So the TC also, or T core, sometimes they write, that also goes as degree 2 scaling. But there is another part, that is your VEE minus J rho. So that is Coulomb part.
But the TC
And
is,
that Coulomb part will go as 1.
yes.
So the together, when you are mixing and telling this as the total correlation, it would be somewhere in between 1 and 2. One part as 2, another part as 1.
But there is no way to actually physically distinguish between those.
No. They are coming from two different origins, totally separated there.
In the functional, like when you get a correlation in it, can we somehow
Which one?
like which part is from the TC part and which part?
No.
It's not necessary, because what you are doing anyway, you are mapping one non-interacting with the interacting system. So whatever ignorance is there, you dumped into EXC. So that is the funder.
See, what is happening is the Lagrange multiplier way, when you are minimizing this kinetic energy. So, no, this variationally when you do this thing, total energy, then this kinetic energy somehow it's coming exactly kind of thing, non-interacting. So no, what I am telling, if you have this scaling thing in, suppose my effective potential is very good, then this correlation is doesn't make any. Yes, that's what I say.
I think the point being made that this is how it should behave. That's okay. I mean, the point is well taken. In between. It's just now and then.
If you look at this orbital free DFT, this is there.
They have a form.
They have free, all the orbital free DFT, you have kinetic energy functional. Now they are doing this machine learning also. We have a couple of papers, this orbital free DFT. That's why I'm not going to that part. This is for constraints. I wrote initial constraints for exchange correlation. Keeping in mind the exchange part is more this thing. Because we never bothered about double hybrid, we bothered about correlation. There we have used this MP2 along with this thing, that is okay. So now this is the iso-orbital limit. Okay. So as this is, you are using the fictitious single particle system. Okay. So it matters that what exactly you are doing, your kinetic energy, then your one electron limit, it should be like your kinetic energy, whatever you are getting, that should be same as the this is Weizsäcker term. Then that is in one electron. So these are the things. So in one electron, if you have the exact Hartree-Fock energy will be same as the exchange in one electron bit. Iso-orbital means one orbital. Okay. So there is this parameter. Yesterday we are telling this alpha T minus TW by T uniform kind of thing. Okay. So this will always be 0 for iso-orbital kind of thing. Okay. So in that case, if there is some violation of this iso-orbital parameter, then there is this problem of this. It is also there are different types of gap, fundamental gap, optical gap, okay, and all these things. Okay. So here means, so when you are exciting one electron. Okay. Suppose you are dealing with n plus 1 system, n system, then the derivative discontinuity and all these things. And then this one is more important, this isoorbital thing, it talks about the localization thing, okay. So that it will, so this quantity is something, this helps you to take care of something called the derivative discontinuity, okay. So which is very essential when you are using this thing. Derivative discontinuity means whenever there are functionals, you are taking functional derivatives. Then when you excite one electron or adding one electron, but you are doing a calculation with a fixed number of electron, okay. During the calculation, you are not doing n for n as well as n plus 1, okay. So you are doing independent calculation either for n plus 1 and n minus 1 kind of thing. You are doing for n and you are thinking for n plus 1 and n minus 1, okay. So that is the thing, and that it has also this connection with this Janak's thing, this del E by del Nj, okay. So this isoorbital here I have not mentioned, so it's basically the localization thing. So there is another quantity called electron localization function, okay. So there, so it is helpful for all this one electron thing, it will be helpful. Derivative discontinuity means you are doing this thing here. So whenever you have done this Weinberg cone, you have this V and then this one, okay. So you are having this thing to H rho, okay, because you are doing this thing. For any many-body system, to define the Hamiltonian, you have to know the potential and how many number of electrons are there. And this is through quadrature, you can have this thing integrated, this thing is to n. So that's how you are first, if your Hamiltonian will become a functional of a density, so this is the thing. And while you are doing the SCF calculation, so this is you are doing for one electron. Now, if this is the thing, okay, so this thing gives me this E rho, energy as a functional of this quantity, or you think some physical variable O, which is a functional of rho, okay. So you can think of atomization energy, enthalpy of formation, reaction, barrier heights and all these things. And when you do this one, suppose I have these things, yes, I have an electron here, say I have electron here, then so there somewhere my formula will be there, and these are the virtual orbitals. I'll say I'll take this electron here, okay. I can take directly here to here, or I can do spin flip and put it like this. So there are two types of excitations, spin flip and charge transfer, okay. So either I'm flipping and taking, okay, singlet to triplet or something, or I'm taking from the same spin is going to this thing. And so far we are talking about this charge transfer thing, and spin flip I never came across like after this Dew shimmer kind of thing. It has a lot of connection with this time dependent DFT. Now when you do this thing, so what you are doing, so my energy is now a functional of n, how many number of electrons. This is my SCF calculation I am doing. Now when I am taking an electron from here to there, how many electrons are there? Now n minus 1. But if I do the SCF way, I have to go here as if I have to think there is this electron is still there, and I am putting one electron here. So that is n plus 1, and but actual scenario is n. So it is n and this is n minus 1, this is n plus 1, okay. Then you are having what? E n plus 1 and E n minus 1. These two things are fictitious now, okay, but you are having En here, okay. And now this energy, while you do the calculation, I have to write down the Vxc rho. This energy, inside this energy there is this exchange correlation energy is also there, okay. Exc rho, then let me write Exc rho n, whether it's for n electron, then E xc rho n minus 1, E xc rho n plus 1. I have to calculate the functional derivative to have the potential to put in the quantum equation. So it will be del Ex by del rho, del this thing by del rho, del this thing. So it will be like V xc with n number of electron. So let us put it like here, n superscript. Okay, here V xc n minus 1, V xc n plus 1. But you are doing a calculation with this virtual thing. This is not true. And this behavior, okay, if you look at this behavior is very different. There is no, so it's not a continuous thing. You are having n minus 1 electron, and n plus 1 electron. Okay, so it's basically you are having del E upon del Nj. Okay, this is called this Janak's theorem. Okay, this J means how many, not exactly Janak's theorem, but this J you can think like that, this virtual orbital thing. So there is a discontinuity. Okay, this whole epsilon J, yes. Yes. So you look. But there is a communication between both of us. So, so that is important. Okay. It should have been. So many you made a mistake. You should have told us that whether you want to have this board thing or this thing. I would love to this thing to do it on board. Okay. So that is not Professor Subramaniam also informed. That is a big mistake because we are a very good board worker. No, I never used this notes or books because of him. I used to stand in front of the board for 5-6 hours. So he'll. No. So that is the thing. Okay. So this thing, if you look at this, what is that? Direct band gap, indirect band gap. It has a connection there. Okay. You have here. Why this bands will go down? It will go up. You write down this thing. You plot this thing. Then there will be this thing. You look at this a primer in density functional theory book. Okay, lecture notes in physics Springer. Okay, Carlo Phileas and all these people. Okay, that is the thing. And this is also you have this thing, and how will project this one out? Okay, suppose you have HOMO and LUMO, that kind of thing. Okay, also your singlet, triplet, this degeneracy, why this degeneracy will be lifted, why it won't, how will connect it to the derivative discontinuity, how will take care of this derivative discontinuity means something is changing. So this derivative discontinuity is a very good thing actually. Indirectly, this is nothing but the derivative discontinuity. But he has never raised this issue. Okay? Because he never wanted to go to the Sam Sutler thing, John Purdy. He wants to have his own thing. That is the thing. He never talked about the derivative discontinuity. It's actually derivative discontinuity. Okay? And you are doing all this GWBSC and everything you are doing, RPA, all these things. Why don't you focus on derivative discontinuity and squeeze that one? Okay? Squeeze that one inside the functional. It will automatically work. And there is expensive, so expensive. I don't know for chemistry people you are doing. We use your data for fitting our things. But the GWBSC, I don't know, maybe it's because of this Berkeley thing. I don't know. What is that? Yes.
Orbitals and eigenvalues that you are using. So if your
starting point itself is not accurate. That GWB.
Then GWB, yes.
And then again there is a fully self-consistent
I
steps are there actually. I mean, but still in solid state physics, still it is considered like a gold standard method to compare in absence of experimental data.
yes, but I have not talked about this thing. We had a functional. This is recently under review. Let us see how it is coming through. But there we are doing one-shot calculation and getting it. That is the intrinsic dilated dependent hybrid one-shot calculation. One shot. And that is in a review in PRL. Let us see. Starting point is good because with the functional we are using, that RMGGC, that functional is also by us. That there we never worried about these constants, but when you checked, it's satisfying everything. That is, I'll not say it's ground state. Somehow you are going some quasi-excited state. That's what I'm saying. I'll not say it's a ground state. Anything else? Sorry. So this is the derivative discontinuity. Now the correct low density limit. Density low means your rho goes to 0. If your rho goes to 0, then the reduced density, this one. What is that? This one. The grad rho upon 2kf rho. So it will go to what? Rho goes to 0 means it will be infinite. Okay. Then in that case, how it should behave? Okay. Although I have this slide, I'll send it to Samal. He will share with all of you. It's not clearly visible, but I wanted to tell you this thing. Then you can use this slide if you are interested. Okay. So this one we use like anything. Okay, to have this inhomogeneity and all these derived things. But now this is low density, high density, what is happening? So that is also important. Okay, and if it is violates, then these are the problems. Okay, so it is because this overbinding, underbinding, overestimation, underestimation, all these things comes in. Okay, so if you are far away from the, suppose you are having a finite system, okay, clusters, and you are like extended systems, okay, and suppose say the extended system is not periodic, non-periodic, and suppose you are having electron phonon interaction and all these things are there in condensed matter, it will come, then there is the problem. Okay, extended system, I am saying, suppose you have defects and other things, say surface defects. If you are doing MD, suppose I'll have say silane molecule with silicon with say 147 silicon atom, then I have some zeolite coming in and interacting, and that is the problem. Because because this work I started in my postdoc, so far no one has published. I don't know this thing. Solid state MD you do, why? That's why I said non-periodic. You are using periodic thing, that's fine. Augmented plane wave and all this projected. Yes, it's a hybrid model. Cluster, then you say a fullerene on the sitting on the surface of the something. Yes. Now, size consistency. This is very important. While you dissociate a molecule, okay, this is very important. And then the fragments are far away when you dissociate the molecule. Then what will happen? Suppose there are two there are two types of atoms of forming a molecule, then the exchange correlation energy, this should be like this. If there are n such things, this will be like this. Okay. Now, if the size consistency will be violated, then it will have very bad behavior. Okay. So the size consistency is in fact this is like you have say a carotenoid, porphyrin and fullerene kind of thing. You are having a charge going from here to there. So there it matters a lot. The size if your functional will be size consistent, then it will give you good result. Otherwise it will not. Okay? So that is the thing. This is also the size consistent thing. Okay? Now comes the gauge invariance. So this wave function, if it will go like this, if you have this density and other things, okay? If you have the wave function goes like this, then what will happen? Here you have phi, then you have some gauge here, okay? Then what will happen? So this should also remain same for the functional should be gauge invariant, okay? Because you are dealing with this density, okay? I can have several ways of these wave functions, but my density remains the same, okay? But if you go inside these wave functions, something else is happening, okay? That your wave function, your density functional should have that in the memory, that this is something happening. Even if I am doing this, even if I am doing this in terms of density, but during the SCF calculation, you have this quantum orbitals and other things. The functional should remain gauge invariant. You can have, there is something called constant source. I can have many wave functions giving the same density. So it's another way of looking at the gauge invariance is like variationally if you are doing something, and then that will have the consensus formalism of Levy-Liev. Yes. Yes. Doesn't come. But you are using this orbital picture like anything. Yes. No. But that is that is we wanted, not that way. First, no, that is there. It's, I mentioned somewhere. No? It's, oh no, that is I forgot. Here, yes, yes. No, that functional should be gauged. Totally energy, yes, it should be in principle. Because the total energy, if you think you're taking a expectation value kind of thing. Okay. If you calculate this, that is another thing also. We are not looking at how this expectation value is being evaluated in terms of cone-sum orbital. That is very interesting. Suppose you have spherical density, non-spherical density, okay? So there, suppose instead of say this exponential, it's perfectly cancelling. Suppose I have something else. Exponential, say E exponential, no imaginary thing will be there. Then that is the problem. Here is imaginary thing, you have something. So that is thing. It is actually the whole thing is
What exactly is the gauge transformation?
the wave function.
So, for example, your Cone-Sham orbital.
Forget about cone-sum. You just give me some density, I can have some mathematical function. You think in terms of constances. For you, you think in terms of constances. Don't think in terms of cone-sum.
But what am I transforming?
This thing, your wave function, if you look, that is transformed, but your density remains the same. The density precision, anything derived from density, that remains the same, but the wave function is doing something else.
In the Levy constraint search formalism, for example, should we not say that this is not one of the best wave function that we should be looking for? For example, search for the best density, then we find the
No, no, we are not bothered about the wave function. What you are saying that you are using the exchange correlation functional to do something. Na? Suppose I'll do some molecular orbital calculation. Okay, there I should have some picture. Why we are worried about the Koopman's thing earlier? Means we are doing these things. So you will say, even if the quantum orbitals are unphysical, still I would like to see. So if you plot for say carbon atom, you plot the quantum orbital and you see that is perfectly coming like this quantum thing. Okay, so that is the thing.
But I think his question is still remains that if I'm doing constraint search
Yes.
and if I transform a wave function
Mhm.
with
This is some gauge.
dependent phase, the kinetic energy will change,
Yes.
and therefore the energy will change. It is not the best function. So why do I even worry about it?
Which the kinetic energy.
Yes, will change.
Mhm.
So it's not. Is that what your concern is? So his concern is that if I do the minimization of the energy and if I include a wave function
Mhm.
which gives the same density but has a phase which is R dependent,
That affects the kinetic energy.
so kinetic energy will go up.
Yes.
If kinetic energy goes up, it's not the best possible wave function. So why am I even worrying about such a condition where keeping a phase doesn't really matter? It's not an acceptable wave function anyways for the ground state. That is what is concerned.
But these wave functions you are using, like you are doing this GWBS.
Understood.
Yes.
But on conceptual ground,
Mhm.
I think then if you are not accepting any wave function, why should I even worry about invariance with respect to that wave function when I'm making an exchange correlation functional?
Yes.
Is that what your concern is?
Yes, so I'm saying this is the thing, because there are many things where you are using this density functional wave functions, that's the starting point to do model Hamiltonian calculation. Yes.
Then you try to generalize it where you can use it in some other place.
No, in our case we have not done this gauge invariance,
Understood.
but for his functional he wanted that my scan thing is gauge invariant and it can be used properly with this GW and other. Yes.
Like tell them this is the required constraints for any arbitrary exchange correlation energy functional to obey this gauge invariance. There must be some proper rationale. I have my own functional and that is obeying gauge invariance. It can obey many other things. It doesn't mean that you can put this as a constant for other functionals.
But the
Why are you
Jacobs
creating trouble for others?
See, the Jacobs ladder also he only gave. Okay, we cannot defy Becky and Purdue. Like you cannot defy par. Okay, that is the thing. No, but Bouquet is not. No, that is the thing, because in our paper we never
You're just discussing what you said. That's what.
Yes. No, we are not discussing. It's globally accepted. Okay. Now this Gellium surface. This is again this for surfaces why it will work. Okay. So it's like if you have calculation for slabs and other things, this MD simulations and other things. Because the scan functionally is used like anything in molecular dynamics simulation for solid state thing. Okay, so it's like you are going for ball to surface, then how this is behaving, and there is another. This is a surface exchange correlation thing here, the sigma xc. Okay, so this.
Exact Gallium surface energies exist.
I
Because then only you will be able to compare.
no, but it is.
So what does it mean that should give surface information energy? Because then they should exist somewhere, maybe some OPM or something or something.
Theoretically, I don't think, but experimentally you have.
So, that's what.
Yes, but theoretically it is not there. It is done, but it will be. Why not? But I have no idea. I don't want to comment. But I never worried about this. नहीं नहीं खत्म हाँ okay next is intermediate range behavior. So it's like 2D van der Waals heterostructure nowadays you are listening. Okay, so intermediate, so it's a weak interaction, strong interaction, and there is something intermediate. Okay, so in chemistry people they talk about this Grimm's functional dispersive, DFT, D3, D4, all these things. But he say this intermediate range means so how it will behave like this C upon R6 kind of thing. Okay, so that is the thing. So he said that for intermediate range it should behave properly. That is the thing. Okay. It is khatam. No. And then what is the numerical stability? Okay. What is the smoothness of the functional? So it's not like you use any functional. Okay. It should do your job. Okay. Many a times you run calculations. You took the cluster time. Your guide will be shouting at you. You are doing this. You are not. Many myself also. Okay. I got like this Minnesota supercomputing.
When you talk about numerical stability,
Hmm.
what do you mean by numerical stability of a function? When you are applying a functional inside consum,
Let me tell you, there are several things we are calculating numerically. This is the kinetic energy. If you
that's why I'm telling numerical calculation only. That is for the self-consistent consum solution where you put this function.
yes.
We are only numerical stability.
Mhm.
The function itself has nothing to do with numerical stability. It will have a formula numerically.
But yes, but you can, but I cannot give some formula. Huh?
Question of numerical stability.
But yes. Yes.
Computed on a grid that consum.
That's what. That is the point. No, that is the point. So anything you do, so you have to do consum. Okay. So means all of us will now gather and come up with.
You see, this is a connotative stuff.
Uh,
If I tell that
My exchange correlation functional should be numerically stable. Connotatively, this is not true. Actually, exchange correlation functional, when I put it in the consum equation and then solve, the numerical solution of the consum self-consistent solution should be numerically stable.
okay. Yes. Yes, we agree. So that is the thing. So let me. No, they will make the functional.
then you check all the night will go.
No. What I said, no. I wanted them to. I asked them if there are 4-5 students, then they will help them to see. Say they will use PB.
What are you doing? What are they doing?
No. My thing is that we'll decide what we'll do. This is the talk. Now they have to tell me what they want. No. They will tell what they want to see. They have to tell. No. They can do. So no. What I'm saying, yesterday I told, na, you pick, you pick a functional and check all this. Say you start with the PB int and do.
No, I'm telling you, about
Years back, so myself and Sapan Ghosh, we used to go to TIFR for computation 40 years back, remember? And your TIFR, yes. Now, in every paper we used to write that although we know that every property can be written as a density functional, it is proven by Hohenberg-Kohn theorem, but unfortunately it is an existence theorem. This was common lines, all papers. Unfortunately, the exact form of those functionals are not known. Then something we didn't write, but fortunately they are not known. That's why you could publish our papers. We have given many functionals. Fortunately, it was not known, but we used to write in that paper. Unfortunately, many papers you can see the same language by many people. Unfortunately, the exact forms are not known.
They are going to check different functionals for all these.
No. I want them, there are several kinds of students. I want them, let's say they will use a functional which is good for molecule, some functional which is good for solid, but they do not. So that's why I asked if there are 4-5 students who are comfortable with this NWKM, they can pick two functional. Let us pick two functionals. We know which is works well for solid, which works well for this one. But let us do that calculation, say for some SCF calculation, say for sodium. Okay, those people will help them, and they should see the difference. If it's a do functionals, what kind of result is giving.